So our next speakers, we're going to be doing the end of object inheritance and the beginning of a new modularity, presented by Augie Fackler and Nathaniel Manista. Please give them a warm round of applause.
Thank you, and good morning. Thank you for coming. This is my friend Augie. He's a contributor to Mercurial.
This is my friend Nathaniel. He's a contributor to Pylint.
And we are here to tell you about the end of object inheritance.
So we've got three premises we want to talk about briefly. These are premises that we think should be uncontroversial and everybody should agree with, but we should state them clearly because we're going to rely on them very heavily.
The first is that we use types for nouns when we're talking programmatically, when we're talking about data that we exchange, when we're talking about components that we rely on. We refer to our nouns using types. Now, they can be formally declared as types in a static language, or in a dynamic language like Python, we may talk about properties or attributes that we expect subsystems to have, or methods that we expect them to support. But we use types for nouns.
And the second is that we prefer to express ourselves structurally. And when we say structurally here, we mean in code, not out of the code in comments, which you will only believe half of the time, or in doc strings, which you'll believe maybe 3/4 of the time, but actually in the shape of the code, which you have to read to understand what's going on.
So we could put all of our code in one giant directory, or all of our code in one giant file. We choose to put our code into subdirectories, into structured layout. We could put all of our functions equally available in one global namespace. We choose to use visibility to say some are more prominent, some are more private.
And in Python, this is just a social convention, but tools like Pylint still catch this and scold you.
And we could use goto for all of our control flow, but we choose to use more sophisticated control structures like if and for. And what's curious is that as control flow has evolved over time, it's gotten more sophisticated with more expressive ways to express ourselves. And for else is really on the cutting edge. I'm a fan, Augie's not.
And most of the programming we do is in some way partial. It's parameterized on some inputs. You're not writing a function that just does something or a long script with no control flow at all. Your modules of your code take inputs that change their behavior in some valuable way.
So if you have a function, that function takes arguments, its result in its behavior depends on those arguments. If you're writing a module, you have dependencies. There are leaf nodes in programming. There are things like the value of pi or a string literal. But almost all programming we do that's really interesting programming is parametric or partial in some way. Now, these three things are things that we believe are not only true, but they're virtuous. They're things that we believe ought to be true. So we're glad that they're true.
And a brief note on visual terminology. We're going to have a lot of components in this talk because we're talking about inheritance or not using inheritance, and we need to rearrange layers of some software. So we're going to have a simple visual grammar that we can all understand.
When you see an open symbol like this, that's going to represent some abstract specification of behavior. And when you see a closed symbol, that's going to represent some concrete implementation of that specified behavior.
And then we're going to use shapes to represent different unrelated behaviors. And the shapes themselves are not important. This isn't Object-Oriented Programming 101 where we're implementing a square and an octagon. We just need these shapes to help you know what part of a slide goes with what layer of the stack we're talking about.
So the other day, we're programming. And because it's a normal day of programming, we're doing some sort of partial programming. And the problem we're being asked to solve is this. We're asked to implement this abstract type. And we have a three-stage process that we know how to do to perform this implementation. Now, the first stage we know how to do. It's filled in, it's concrete. We know how to do that first stage of our implementation. The second stage, we have to leave abstract because we don't know how to do it. That's something that a client or a user or an extending subclass is going to tell us how to do. And once they've done that, we know how to do the third stage of implementation. So that's concrete.
And so in orthodox inheritance, this is roughly the solution you'd probably end up with, right? You've got this abstract base class. It's got some method or methods for the lowest layer, that blue square. It's got some method or methods for the top layer, the octagon. And then it has this abstract piece in the middle. And a client of this code is going to look something like this.
Yeah. The client of this code is going to have no reference at all to the blue and orange layers as implementations that they've defined, though they may call the blue methods, but they're going to provide a concrete implementation of the green method.
And so this is a little bit disappointing because we have to tell all of our clients about the three-stage implementation in pretty great detail. And that happens only in annotation. Visibility kind of helps a little, but the orange method in this example might be the actual public, useful thing that this class does. And so it's going to have public visibility. I actually don't know of a programming language that could hide the orange layer, the top layer of this solution, from the green method if they're on the same object. Public is public, and anybody can use it, including members of that object.
So visibility helps a little, but we still have to export to our clients, to our implementing subclasses, this notion of a three-stage process, and that they're allowed and encouraged to call methods from the blue stage, but discouraged and forbidden from calling methods in the orange stage. And the mechanism that we use to do that is documentation. We say, hey, look, in our abstract specification of that second stage, that green stage, you're not allowed to call orange methods from here. You're not allowed to call things that we intend to come later.
And so classes might not even do this. They might say, this reserves the orange reserves the right to call the green layer, but it does not at this time. But if you do, it's going to go bad for you later, maybe. And this reminds us of American politics.
So we have this we have this bumper sticker culture, we have this soundbite culture, and one of the critiques of American discourse that I really like, it's unfortunate, but it's true, it's that if you're explaining, even if you're right, if you're explaining, you're losing, right? This inheritance-based code that we've just gone over, this is right. It solves the problem correctly, but it's explaining, and so it's losing. It's using that out-of-band documentation channel.
And that's a practical problem, right? And we can overcome this practical problem with a number of solutions, right? You can mentor new people on a team, have more experienced people working on the lower levels of a project, have conventions, but that's not the only problem we're seeing here. There's also a more deeper-seated theoretical problem, which is we're violating our first two premises in order to fulfill our third premise of having a parametric program.
All right, who remembers premises 1 and 2? Anybody taking notes? All right, good, thank you.
Right, we're not expressing ourselves structurally, and we're not using types to organize. In particular,
the stages are nouns, right? I talked about them as nouns. I said this thing has to come before that thing. This thing is allowed to access that thing. Those things are things. They're nouns. Give those nouns some types. Nouns love types.
And what's more, the implementation stages are actually structure. We said that the blue layer is dependent upon by the green layer. There's a relationship there that's only being expressed in our documentation, not in the structure of the objects in our code. So going back to this one more time.
Before we move on from this, this may have looked contrived. This may have looked sort of like a special case that we cooked up. I actually believe this covers all generic, non-degenerate cases of inheritance. Maybe you don't have 3 layers. Maybe you just have 2 and the bottom's abstract, or maybe you just have 2 and the top is abstract. Or maybe you don't have 2 layers of methods. Maybe the bottommost layer of your inheritance case is your object state and its fields. But if you're using inheritance in some non-degenerate way, where you have some methods that call other methods and some methods supplied by superclasses and some provided by subclasses, we believe that you fit this picture and that you're covered by the grievances that we've articulated.
And so we're looking for a way to accomplish the same 3-stage task. We're not going to change the algorithm in principle, but we're going to change the shape of the code so that it actually satisfies all 3 of our premises. And that solution that we found is composition.
How many of you have heard to favor composition over inheritance? Wow, that's actually a lot fewer than I expected. Okay, well, let me introduce you to the idea if it's new. We weren't prepared for that. We were prepared for you to already have accepted this idea and for the argument to be underway, and we're here to conclude the argument. We're here to pound the final nail in the coffin. So for those of you, I'm glad the process has started, and for those others of you, this is going to be a very quick personal transformation, but very dramatic.
So composition means instead of inheriting, we're going to pass one layer into another, right? We like this because it's an explicitly one-way relationship. In that object-oriented example, you might have bidirectional communication between the layers of that solution. Maybe the green layer and the blue layer have sort of hidden communication through attributes on self. And that's really not what you wanted, because we said, there's this relationship. The blue is dependent upon by the green. There's a one-way arrow when I describe it in English, but there's a two-way arrow in my code. And so the solution looks more like this. We have a module which defines these three interfaces: the blue interface, the green interface, and the orange interface.
We've given types to every noun that we're talking about.
And then the two concrete types that we're, as the module implementers, able to provide, the blue and the orange, the bottom layer and the top. The blue method takes no parameters. The blue object, the orange object takes a green as a construction parameter and then has the methods that it needs to export. And then the client will just implement one class like this.
And they may not necessarily need the blue. All we need for them is for them to implement the green type that we've said. That's all we need. Now, they may rely upon the blue earlier type if they fit into our three-stage process, or they may optionally just opt out of it.
Yeah, they may be doing something that we couldn't anticipate. And so this is actually more flexible without them having to know details of our implementation, which we think is great.
Yeah.
Sometimes your interfaces are going to overlap. You're defining a lot of types at this point, and not all types are completely disjoint. And so one of the nice things about inheritance is that you can share method definitions between things very easily. And I'm willing to say at this point that that's not actually a virtue, because when you need to follow what's going on, you need to figure out, oh, I'm calling this method, and in our inheritance example, you're actually going to have to look at the abstract base class for the public method, the orange one. Then look at the green class to find the green implementation, then look back up along the method resolution order to figure out what's actually being called. Delegation, where you're just going to write a one-line function that says, oh, I need to export this thing off of green, def foo, return self.green.foo, makes that very explicit. It's easy to read. You don't have to worry about manually tracing something that the interpreter is going to figure out for you at runtime.
Now notice, these solutions are both right, but in this latter solution, we're also not explaining, and that's winning. We want to compare these two models also in the context of fault tolerance, right? They may look equal, and they may seem equal because they're equally performant. They have equal algorithmic complexity. The fact that it might seem like when they're correctly implemented, they're both perfectly equal, may seem like they might be a personal choice. You might get to choose whichever one fits your personal style.
And when we're talking about fault tolerance here, it's not fault tolerance of a running system. That's a virtue. But the virtue we're looking for is fault intolerance.
And they are radically different in software architecture fault tolerance.
We want things to fail as soon as possible. We're thinking parse error or compile error. You want feedback to you, the programmer, that you've made a mistake as soon as possible, instead of ending up with an infinite loop or some other means of the error silently passing unremarked.
Right. So the faults we're talking about is Augie is writing a system and I'm collaborating, and we've chosen one of these two models and I make a mistake. How is the model going to respond to my programming defect? Not an execution defect like a network failure, but a programming defect like my breaking some abstraction in our architecture.
So object inheritance really fails to be fault intolerant.
If an extending class calls some method that is available to it, but that it architecturally should not be calling, you could get a bunch of different things happen. You could get your state corrupted, you could get an infinite loop, or if you're in this situation where the base class reserves the right to call a function but does not do so at this time, you could have code that runs perfectly well until you upgrade your library a year later, and all of a sudden it starts failing, and you're at a loss for why and where to look.
And you spend 3 hours debugging, and you finally end up in that state we've all been in, where you look at some code and you say, how could this possibly have ever worked? Whereas with composition, you'd have none of these problems. It's impossible for the higher layers of the stack to accidentally reference the lower layers. I mean, you could do it, like defining a closure and referencing things and enclosing scopes.
And you can do anything with reflection.
Yeah, but your code's going to look so funny that your code reviewer, which I hope you have, is going to tell you that you're being bad. Or you're going to look at your code in 2 hours and say, wow, that's really not okay. I should stop doing that.
If you're using this pattern and you make a mistake, you'll be stopped early, and that's great.
And this is related to something that's made its way around the sort of data modeling world of making illegal states unrepresentable.
And so this is like choosing to use an enumerated type instead of a generic integer, choosing to use a combination of Booleans rather than like a bit mask represented as an integer. We're arguing something analogous, which is that you should make illegal behavioral interactions impossible.
And composition manages to do this fairly easily. It just falls out onto the page for you. Whereas with inheritance, it's actually something you have to reason about yourself as you're writing the code. The compiler can't give you help, and your colleagues might be able to give you help, but in practice, we're all humans and we miss things.
You have to work, you have to communicate, and then you have to convince your inheriting and extending subclasses to respect your choices. It's a lot.
And this means that you're going to end up with a lot more small objects. And the first time I heard this, it was advice along the lines of, wow, that class is really big. You should make it smaller. Or maybe even Pilot saying, this object appears to have too many attributes. You should rip some of them out. And that kind of bothered me because it just sounds like I'm going to tear my code asunder in weird places. And that's not what we mean.
Right, we've all been told this code is too big, break it up, I don't know how. And coming from a mentor, that's really poor advice because the listener doesn't know how as well. Well, we're here to tell you the right way to break up code into small methods and objects. Break all bidirectional relationships. I haven't theoretically proven that bidirectional relationships are never necessary, but in 10 years, I haven't seen one that I haven't been able to eliminate.
And I became really convinced of this in some code at work where we were collaborating, and I kind of squinted at it and said, man, that's going to be really hard. We have to figure out how to break this dependency. And what Nathaniel did was he actually broke two objects that were mutually dependent into 4 objects that had no mutual dependency. So one layer became 2, and the arrows started pointing only down instead of sideways.
And then once you've eliminated your bidirectional relationships, unidirectional relationships are not virtuous, right? The choice between having no relationship between two subsystems and having a simple relationship between two subsystems is have no relationship if you can get away with it. So minimize your unidirectional relationships.
It's related to sort of the Unix philosophy of doing one thing and doing it well, right? You want these objects that are as small as possible and do one thing very clearly that are then pluggable into other parts of your system.
So this is what motivates that premise that we started with at the beginning, right? We prefer to express ourselves structurally because when we do, we make illegal behavioral interactions impossible. And that's great. I love being freed up from an entire class of defects simply by having chosen to program in a certain style. That's great.
And if you adopt this thinking, your code's going to start changing. And it's a gradual change. It's not going to change immediately. But you're going to define types everywhere. And when we say types, what we really mean are these abstract types, collections of behavior, a Java interface or a completely abstract class in Python.
You'll find yourself talking about nouns, right? Because you can't avoid talking about nouns when you're talking about programming. And you'll find nouns in unexpected places. You'll find like 3 nouns in maybe the interface of what had been a single concrete class before. So you'll define a lot of interfaces, especially at your public API boundaries between modules, but also they'll turn up internally to your modules as well.
And your clients will start using your interfaces, not your concrete classes. You'll probably start with some public classes, but over time, your public classes start evaporating and sticking out in your API because the only thing your public class really offers beyond the interface it's fulfilling is some means of construction.
And construction isn't so idiosyncratic. It isn't so special that it deserves to be there. If your clients are saying, you've described several types to me, and I've expressed my code in terms of those types, and you've made several functions available to me, and I've expressed my code in terms of those functions, but the construction isn't so special that it doesn't just deserve another round of functions. So your constructors will evaporate and mutate into factory functions.
And factory functions are they sound kind of like a Java thing that we in the Python community might make fun of, but they're actually really useful, right? Because maybe you write some library for loading resource files off of local disk, but you don't really care that they're local disk. Maybe in a year they're going to be loaded from the network. So you just have a function that, given a resource name, loads the resource and returns it to your client. And next year, you're starting to load them over HTTP, so they just provide you an HTTP prefixed string instead of a regular string. They're getting, a network resource instead of a local resource, but it doesn't matter to their code because they're using the interface you specified that only defined the interesting behavior for them, not the implementation details you cared about.
Factory functions just mean that your module has become responsible for instantiation the same way that your module is responsible for everything done post-instantiation as specified by the types that you have declared.
And this means your modules will just transform into collections of abstract types and functions that operate on those types.
Now, this may seem like degeneracy. This may seem like de-evolution and a step backward. If you go from frameworks, if you go from very powerful concrete classes down to just a collection of types and functions, that may seem like a simplification. We believe it's a virtuous simplification, that it is the most client-friendly and most user-friendly way of expressing the public API of any module. You should not be surprised if some of your functions wind up being very, very powerful. Right? The process that I introduced at the start of this talk was, I said, I have a 3-stage process, and I know how to do the first stage, and I know how to do the third stage, but I need some extender, some client to tell me how to do the second stage. And this is that process expressed as a function, right? We say, if you provide the input type, which is the first intermediate type, if you provide a way to get from the first intermediate type to the second intermediate type, and that is to perform the second stage of the process, then I can tell you how to complete the overall process and return the final result, right? I just took a lot of English prose to lay that out, but look at how concisely it appears as a function type. These are the kinds of functions that you're going to be providing, and it's great.
And you'll probably have value types kind of peeking out of your interface, the public interface for your module, and that's okay. These dumb data objects don't really provide any behavior. They're a way of bundling together related information. Nathaniel likes to sweep them away too. I found that leaving them exposed is generally fine.
So we've now taken you to the point where all of your modules are self-contained, they're isolated, they're testable, they're independent, and that's great. But we don't build applications out of single disconnected modules. We assemble modules together to make applications. We assemble simpler behaviors together to make more complex behaviors. And right now, this picture doesn't solve that, right? The input types of all these modules and the output types of all these modules are all exclusive. We need some way to bind them together.
And so to motivate this a little bit, we're going to take a slight detour. How many of you remember this gentleman?
Good times, right? Good times.
So Mr. Rumsfeld had a way with words. These fascinating, 1 or 2 sentence nuggets that you get a parse error like the first 3 or 4 times you read it, and then you finally get to a point where you've evaluated the sentence and it's either vacuously true or something really deeply philosophical, or maybe even both. And one day, Nathaniel, around the time of that same example of breaking a circular dependency, announced that we were practicing anti-Rumsfeldian software design. And I had no idea what he meant, because there's one Rumsfeld quotation that you're probably all thinking of, unless you're stuck on one of the previous 2. But he was thinking of this one, which is an interesting sort of reflection on life, right? You're going to war with the army you have, not the army you might want to have. And like that's kind of life advice, right? You drive the car you have, not the car you wish you had. You use the programming language you have, not the programming language you wish you had, unless you're Alex Gaynor. And our question is, does anything like this apply to software? And the answer is that the opposite applies to software, right? We're defining these modules around types. We want to define the modules in a way that's convenient for their own implementation.
So what we're saying is, there are parts of your program that are hard. There are parts of your program that are complex. We're saying you should write the hard parts, the business solving parts, the complex parts of your code, not in terms of the dependencies that you have, but in terms of the dependencies that you wish you had. Not in terms of the results you're being asked to provide, but in terms of the results that you wish you were being asked to provide. Because when you specify your behavior on first-class terms, on the terms in which you conceive of it, your code is going to be more readable and more testable.
And you spend more time reading code than you do writing it. So our case is that these stateless adapters are cheap to write, And they don't really have any logic, really. It's just they're copying from one data form to another, changing the shape a little bit, or maybe hiding the implementation details of some uncomfortable API. It's like using a wrapper around your database instead of writing SQL directly in your source code. You can do the SQL directly in your source code, but now you've got to be aware of the implementation details of the SQL server that you're using, and it's kind of a mess. These adapters let you hide the lower level mess, and that's great.
These adapters let you fit your modules together into an application.
And sometimes you hear, well, these adapters are expensive, they're adding indirection. We found these adapters often make the higher level code more readable and easier to work on in the future. And the last argument you get against them is, I can't define a translation layer. And we found that in those cases, we just defer writing the translation layer until later, because this is a sign that we haven't fully thought through the problem space somehow. And the translation layer ends up sort of falling out of an uncomfortable piece of code, and it becomes two clean pieces of code at the end.
There can also be a problem that if you've defined half of your behavior in one module and half of your behavior in the other module, and the time to join them together comes, and you're not able to solve that problem quickly and straightforwardly, you may not have solved the problem that you actually have. And that's fine, that's learning, and that's a lesson, and you're going to go fix it. But that's not a problem. And so we believe in types, functions, modules being assembled together to build applications. Thank you very much.
Okay, so if we have any questions, please use the mic here in the middle here so we can capture your voice on video.
Did I sound all right? Okay, and questions? Is there?
Howdy.
Over there in the green shirt.
Is this mic on?
Yes.
Yeah.
Fantastic. So I think I'm supposed to say something about small talk, but I think that'd be a little mean, so I'm going to hold it off. When talking about interfaces, are you familiar with any actual strong interface systems like Zope.interface?
I'm familiar with them. I haven't ever used them in Python.
The question is, are we familiar with strong interfaces such as Zopa?
Zope.interface. I've come across them. I've never used them in Python.
They're pretty much exactly what you're looking for, I think. Should give them a whirl. Thank you.
Thank you.
Great presentation.
Hi, I agree with everything you just said, and I wish I'd given this talk because it's awesome. And the question I have is about the other use of inheritance when you have, when you want unplanned reuse. In the case of, I have...
I'm sorry, unplanned
reuse.
Unplanned reuse.
I have a class with 10 methods, and the author didn't factor it properly. I need to get in there and replace a couple of those. Do you feel like that this is a case you should always try to parameterize rather than try to deal with replacing overriding methods?
So the question is about unplanned reuse, and if it's appropriate, given a concrete class of 10 methods, and we only need to replace 5, what should we do in that case?
So my first goal would be to go and refactor the class, right? I mean, hopefully it's open source or it's even part of your company's proprietary source, right? You can go and clean that. If you can't, I mean, you do what you've got to do, right? You either write your own implementation that's parameterized correctly, or you go and you do something horrible. You subclass, you have to write software at the end of the day, and there's always
This is Python.
So I agree with that, and I would say that in a static language, if that concrete class implements some interface and its clients only reference it by that interface, I would suggest that you implement a new implementation of that interface, delegate to the 5 methods of the old class that you use, and put your implementations in that. Now, if you're in a language like Python, where interfaces are sort of implicit, you can still do that delegation, and it doesn't even have, the concrete class doesn't even have to implement some interface.
Right. Yeah. Thanks.
Thank you.
Like you guys, I'm a big fan of passing around objects that implement interfaces, but sometimes that's overkill, and I'm surprised at least Augie, you didn't, as a mercurial hacker yourself, you didn't mention sometimes it's enough to just pass in a function.
So,
what are your thoughts?
The question is, sometimes interfaces seem like overkill. Is it ever enough to just pass in a function?
and often, in fact, most of the time, I pass around functions, not objects. Functions are interfaces themselves, right? They're just sort of an object of only one method in some sense. So yeah, absolutely, pass functions around like crazy. It's great.
Yeah, I would say once you've got the religion of composition over inheritance and you get the idea of passing around objects that just implement interfaces, think about just passing around functions. It's even easier.
So I would counter that to say that I love passing around functions in languages that are first-class functional, like Haskell, like ML. In Python, and especially in Java, where it's a structural problem, but in Python it's more of a cultural problem, I have a hard time documenting a function as an interface. I have a hard time communicating that across an API boundary to a client who may not work at the same company, who may not be of the same mind. And so a lot of the times, even for just an interface of one function, I'll define a class, I'll define a method on that class so that it has a sort of first-class appearance and a first-class notion of currency that can be passed around. But I agree that I favor, in functional languages where you can talk about a function type as a first-class thing, just pass the function.
Okay, so that is the end of this talk. Please give him another big round of applause for an excellent talk.
Code in one giant directory, or all of our code in one giant file. We choose to put our code into subdirectories, into structured layout. We could put all of our functions equally available in one global namespace. We choose to use visibility to say some are more prominent, some are more private.
And in Python, this is just a social convention, but tools like Pylint still catch this and scold you.
And we could use goto for all of our control flow, but we choose to use more sophisticated control structures like if and for. And what's curious is that as control flow has evolved over time, it's gotten more sophisticated with more expressive ways to express ourselves. And for else is really on the cutting edge. I'm of things that we believe ought to be true, so we're glad that they're true.
And a brief note on visual terminology. We're going to have a lot of components in this talk because we're talking about inheritance or not using inheritance, and we need to rearrange layers of some software. So we're going to have a simple visual grammar that we can all understand.
When you see an open symbol like this, that's going to represent some abstract specification of behavior. And when you see a closed symbol, that's going to represent some concrete implementation of that specified behavior.
And then we're going to use shapes to represent different unrelated behaviors. And the shapes themselves are not important. This isn't Object-Oriented Programming 101 where we're implementing a square and an octagon. We just need these shapes to help you know what part of a...
So our next speakers, we're going to be doing the end of object inheritance and the beginning of a new modularity, presented by Augie Fackler and Nathaniel Manista. Please give them a warm round of applause.
Thank you, and good morning. Thank you for coming. This is my friend Augie. He's a contributor to Mercurial.
This is my friend Nathaniel. He's a contributor to Pylint.
And we are here to tell you about the end of object inheritance.
So we've got three premises we want to talk about briefly. These are premises that we think should be uncontroversial and everybody should agree with, but we should state them clearly because we're going to rely on them very heavily.
The first is that we use types for nouns when we're talking programmatically, when we're talking about data that we exchange, when we're talking about components that we rely on. We refer to our nouns using types. Now, they can be formally declared as types in a static language, or in a dynamic language like Python, we may talk about properties or attributes that we expect subsystems to have, or methods that we expect them to support. But we use types for nouns.
And the second is that we prefer to express ourselves structurally. And when we say structurally here, we mean in code, not out of the code in comments, which you will only believe half of the time, or in doc strings, which you'll believe maybe 3/4 of the time, but actually in the shape of the code, which you have to read to understand what's going on.
So we could put all of our code, and Augie's not.
And most of the programming we do is in some way partial. It's parameterized on some inputs. You're not writing a function that just does something or a long script with no control flow at all. your modules of your code take inputs that change their behavior in some valuable way.
So if you have a function, that function takes arguments, its result in its behavior depends on those arguments. If you're writing a module, you have dependencies. There are leaf nodes in programming. There are things like the value of pi or a string literal. But almost all programming we do that's really interesting programming is parametric or partial in some way. Now, these three things are things that we believe are not only true, but they're virtuous. They're